In this video, we're going to be using R to do some simulation again. This time we're going to be simulating drawing samples from a particular bivariate distribution. And then we're going to kind of take a look at what happens if we repeat that process thousands of times and look at the distribution of possible beta hat 1 values and beta hat naught values that we could get when we simulate. So let's start with defining a sample size we want to work with. So I'm just going to pick 50. I'm also going to specify a range of x values for us to work with. So this does matter a little bit in terms of how accurate our parameters, our estimates are, as I'll talk about in just a second. But just for sake of simulation, I'm just going to do a sequence from 1 to 50 by 1s. We're also going to define some parameters for this distribution that we're going to assume exists. So let's say that beta naught is going to be 10. Let's say that beta 1 is going to be 2. And let's say that sigma is going to be 3. So I'm going to define each of these things here. Variance of beta hat 1. So we can calculate what the variance should be for beta hat 1. So again, if we're using a least squares method, we can kind of calculate the distribution of beta hat 1 first. So we know that beta hat 1 should be centered, it should have a mean of beta hat 1, but we also know from the least squares method that the distribution of possible beta hat 1s should have a variance represented by this equation here. So I'm going to run this, and we're going to do the same thing for beta hat naught. So we talked about how the variance of the distribution of possible beta hat naughts should follow this particular equation here. And let's go ahead and take a look at what those values are. So we can kind of see them in the global environment, but I'll go ahead and run them down here in the console as well. So the variance of beta hat 1 is about 0.0008. The variance of beta hat naught is going to be about 0.742. So what we're going to do is we're going to simulate taking samples of size 50, calculating the beta hat 1 and beta hat naught from that particular sample if we do a linear model, saving that, and then repeating that process over and over and over again. And we're going to see what that distribution looks like. So I'm going to do a for loop here. I'm going to do 10,000 samples. I'm going to set we're going to make these beta 0 hats is going to be start from null, and then we're going to do the same thing with beta 1 hats is also going to exist as a null variable as well. So for I in 1 to num samples, or num samples, I never know if I should call it num or num. I guess it's like a number, but it's also numeric, so I guess both of those are valid. And then inside of this, I'm first going to create a vector of 10,000, or actually a vector of 50 epsilons per iteration that I do this. So 50 amounts of, 50 residuals for each particular bivariate distribution. So epsilon is going to equal our norm. It's going to be, what did I call this? It was sample size. So sample size, so I'm going to do 50 normal distributions, outputs with a mean of 0. I'll say mean of 0 to be clear, and a standard deviation of sigma. So again, my my residuals are going to have a standard deviation of sigma. They should have a mean of 0 because they should be centered about the best fit line, and I'm going to do 50 of these because that's how large each of my samples is going to be. Next, I'm going to calculate my possible y values that I could see then, where it's going to follow beta naught plus beta 1 times x plus epsilon. Next, I'm going to create a model of the simulated data. So I have kind of a set of x and y values that follow this equation but have a random error component. So then if I create a least squares spaced model of y predicted from x, I'll get a beta hat 1 and a beta hat naught from this model. And I should call this, you know what I did? Sim model equals linear model of y tilde x. So this will give me some sample or some sample statistics, some estimated parameters based on this particular sample from the distribution. Then I'm going to have my beta naught hats. I is going to be the coefficient of the sim model. And it's going to be, I believe, the first parameter for the intercept. And then I'm going to do the same thing with beta hat 1. This is going to grab the second element of the model. Okay, so I'm going to run all this. I think I'm up to date here. So basically, I'm taking samples of size 50, but I'm going to do this 10,000 times, and I'm going to get 10,000 estimates for beta naught and beta 1. So let's go ahead and check how close my estimates are. So beta 1 we set to be 2, and beta naught we set to be 10. So let's take a look at the mean of my beta 1 hats. And I get almost exactly 2. For my beta naughts, it's almost exactly 10. So that makes a lot of sense. So if I take the mean of all my beta hat 1s and beta hat naughts, it should be centered very close to that parameter. So the reason it's not exactly 2 and exactly 10 is because, again, I'm only doing it 10,000 times. I need to do it an infinite number of times in order to get them to be centered exactly at the parameters. But I can kind of get a sense already that they are centering around the parameter there. Now the variance estimates should be interesting as well. So we calculated what the variances should be for beta hat 1 and beta hat naught here. So it should be about 0.74 and about 0.0008. And I can see that I'm definitely in the ballpark. I'm pretty close to each of those estimates there. And then finally, I can go ahead and plot histograms of my beta hat 1s. And again, I can kind of see that it's normally distributed around 2 with a particular amount of variation. I can do the same thing with the beta hat naughts, where it should be normally distributed around 10. It's a little bit weird at the top. Some of that might just be how many breaks I have, and again, doing it 10,000 versus doing it more times. It's ever so slightly not centered at the very top, but it is about normally distributed around 10. Now, if we wanted to, we could change some of these parameters. So one thing that I think is interesting that we talked about is how the X range can matter a little bit in these calculations. So let's say that the range is the same. It's still going from about 1 to 50, but I'm centering it somewhere different. So instead of centering it around 25, what if I want to center this around 0? So maybe I want to go from negative 25 to, and I'll have to do 24 because 0 is going to count as one of those 50 slots. So if I center my X range around 0, that means that X bar is going to be around 0. So as you might remember, that is going to give me a better beta hat naught estimate if X bar is really close to 0. So everything else staying the same, it's the same range. SXX is going to be the same here, but X bar squared is going to be different. And so you'll notice here that if I change that, keep everything else the same, and then calculate each of these values, notice that beta hat naught is going to get smaller. Beta hat 1 should stay the same there. So notice, yeah, that dropped from about 0.72 or 0.74 to about 0.18. So again, X bar can matter in my beta naught estimate. I could also just make the range a lot smaller. So let's say I go from negative 1 to 1, and I'm just going to make the length equals sample size. That will also work. So it's just going to split it up into 50 equal pieces there. So I'm going to do that and then keep everything else the same. I'm going to calculate the variances again, and notice how these are going to change. They should get smaller for both of them. So beta hat naught actually doesn't get much smaller at all. Beta hat 1 though does get, or actually I'm getting a little flipped around. So what happened? What were they before there? So I had it negative 25 to 24. So let's take a look. So beta hat 1 is going to stay the same, I think. Did I do that correctly? Did I define that? So here's my sequence. Oh, I need to recalculate this. That's the reason. So beta hat 1 actually gets bigger if I make the range a lot smaller. So remember how we talked about if my window's really small, so if I have a really small viewing window, it's harder to estimate these parameters. If my viewing window is a lot larger, then I'm going to have a better estimate of these parameters. So here, I'm going to have a better estimate that way. All right, so I won't do anything more here, but hopefully that demonstration was just kind of helpful and just kind of confirming we talked about that beta hat 1 and beta hat naught have distributions. They're normally distributed, centered at the true parameters, and we can represent the variance or the standard deviation, or in this case it's going to be the variance of each estimate with these equations.